Imagine holding an entire, like an endlessly generating universe just sitting there on a cheap USB stick.
Right, with zero internet connection.
Exactly. No internet, no massive server farms drawing down the power of a small city. Just a tiny, localized machine sitting right on your desk, kind of just dreaming to itself in the dark.
It's a completely different paradigm.
It really is. I mean, you look around today and everyone is talking about these trillion parameter AI models, right? The ones that ingest the entire internet just to, help you write a polite corporate email.
Yeah, the leviathans of the tech world.
Right. But today, we are going in the exact opposite direction. We are going agonizingly small.
And it is a radical shift in perspective. Because we've been conditioned, to view artificial intelligence as this monolithic entity, this thing that absolutely requires supercomputers to even function.
Oh, for sure. It feels unapproachable to the average person.
Exactly. Okay. But when you strip away that desire to build a general assistant, and instead you focus on building a hyper-specialized closed-loop system, the architecture required becomes something you can literally run on a standard laptop CPU.
Which is just wild to think about. And the stack of sources we are diving into today outlines exactly how to do that. I got to say, it is, frankly, one of the most bizarre and brilliant collections we've ever seen on this deep dive.
It's definitely a unique synthesis of disciplines.
Yeah, I mean, we've got a technical conversation transcript that serves as a literal PyTorch blueprint for coding a tiny language model from scratch. Then we have research notes detailing a data ingestion pipeline built entirely out of comic book panels.
Which is fascinating in its own right.
Totally.
Oh.
And to cap it all off, we have a system instruction manual for an execution engine that reads like a computer science textbook written by a mad poet.
I think that's a pretty accurate description, actually. The synthesis here is what makes this project so compelling. You are looking at raw data extraction, machine learning architecture, and high-level theatrical systems design, all intersecting to build a very specific machine.
Right. And the sources refer to this machine as the Clockwork Necronomicon.
Such a great name.
Isn't it? It is a localized, lore-generating state machine. So our mission for this deep dive is super clear. We are going to walk you through the exact step-by-step mechanics of how this tiny language model is actually built.
And we have to constrain it strictly to this Clockwork Necronomicon universe.
Right, strictly constrained. And finally, because, a text generator is pretty useless if it doesn't actually do anything, we're going to figure out the missing piece of the puzzle. We're going to look at how to build an execution engine that takes that generated lore and runs it like an actual operating system.
But to build any system, you really have to start with the foundational material. I mean, before you can architect a neural network, you need to give it a memory.
Right. Where does it get its thoughts? And if we are building a custom, highly constrained universe, we obviously can't just plug this thing into Wikipedia.
No, absolutely not.
Because if you try to feed the entire internet into a model this small, it's not going to learn anything useful. It would be like trying to run a massive, modern, multiplayer AAA video game on an old 1990s graphing calculator.
Yeah, the system would just experience a total memory overflow. It would literally just spit out static.
Exactly.
The parameter count, which is the actual mathematical weights where the model stores its concepts, is intentionally constrained here. So you must be ruthlessly selective about the training data you feed it.
You can't just scrape everything.
Right. The sources detail a process of automated corpus extraction to solve this. So instead of scraping the web, they point a script at a single, highly curated incoming folder of visual assets.
Specifically, comic book panels. Which is such a weird place to start. The folder is filled with images from something called the Uncle Entity comic, focusing on this character named Prime the Glitch.
Yeah, Prime is the focal point.
But this immediately presents a massive mechanical problem, right? A neural network doesn't have eyes.
No, it doesn't see anything the way we do.
Right, so when a computer looks at a JPEG of a comic book panel, it doesn't see a sassy character with spiky hair holding a wrench. It just sees a grid of, millions of pixels. Each one just assigned a numerical RGB value.
The visual data is completely unstructured to a machine. The narrative flow, the spatial relationship between a character and a speech bubble, the background environmental cues, none of that actually exists to the machine.
It's just a wall of numbers.
Exactly. So to train a language model, you need machine-readable text. You have to build a bridge across that medium gap.
And the sources outline using an OCR pipeline for this optical character recognition. And the way they utilize it acts almost like an automated accessibility describer.
It's a really clever use of OCR.
Right. Imagine a script waking up, opening the first image in the directory, and algorithmically stripping away all the art. It totally ignores the intricate line work, the color palettes, all of that.
It's hunting for contrast.
Exactly. It hunts for high contrast edges that form letters. It isolates the speech bubbles and the background signs, and it flattens them into a pure plaintext file.
And you have to understand, it is a deliberate, lossy distillation.
Yeah.
You are essentially destroying the visual art to extract the structural narrative.
Wow, destroying the visual art. That's intense, but true.
It is. The OCR engine is isolating the raw dialogue, pulling out the idiosyncratic slang and the environmental flavor out of all that visual chaos.
So let me read some of the raw text extracted directly from these panels in the source notes, just so you get an idea of the psychological profile we are about to inject into this machine.
The flavor is very specific.
Very. We have lines like, gravity is just a suggestion, man, and so this gravity thing is new. Also, where's my soldering iron?
You immediately get a sense of the character's internal logic there.
Yeah.
He's irreverent, mechanically obsessed, and operating in a reality where the laws of physics are apparently just optional.
Totally. And then it gets a bit more unhinged. We have some all caps extractions here. Iguana on a stick.
Right.
And master of puppets. I'm pulling your strings. This book is sick. Followed by kaiju mode, engaged.
It's chaotic.
Yeah.
And the OCR pipeline takes all of these extracted strings and just appends them, line by line, into a master document. They call it Necronomicon corpus.txt.
Okay, so that's our raw data file.
Yes. The entire goal of this extraction is to capture the essence of Prime the Glitch, his vocabulary, his pacing, his, frankly, erratic mental state.
Okay, so we've scraped the soul of the character into a text document. But if I'm looking at this from a systems engineering perspective, we have a major problem.
Which is?
Well, if we just feed a PyTorch neural network a giant text file of these chaotic, disconnected quotes, it's not going to learn how to build a universe, is it? It's just going to become a digital parrot.
Exactly. We just parrot things back.
Right. It's going to look at the prompt gravity is and just squawk back a suggestion, man. Because that's literally all it knows.
That is the exact hurdle the engineers of this project faced. Unstructured plaintext, no matter how flavorful it is, only produces a parrot.
Right.
If the goal is to build a localized, lore-generating machine like a state machine that can actually dictate what happens next in a system, well, raw dialogue is entirely insufficient. The chaos must be contained within a framework.
We have to format the firmware. The raw OCR data has to be transformed into highly structured mathematical training data.
The blueprint outlines this as dataset generation. You simply cannot rely on raw conversational text because a tiny model lacks the massive parameter count necessary to infer complex logic from casual sentences.
Because it's so small.
Right. Massive models, like the ones built by major tech companies, they can figure out implied logic because they've read billions and billions of examples. But a tiny model, it needs the logic explicitly hard-coded into its training data.
So how do they do that?
So they augment the extracted text by wrapping it in XML tags.
Oh, wow. They force the chaos into a predictable hierarchy. Let me read you the exact XML structure the model is forced to learn from the blueprint. Because the text file stops looking like a comic script and starts looking like this open bracket module ead equals, quote, v1, quote, name equals, quote, uncle entity, quote, close bracket.
It gets very dense.
It really does.
Yeah.
Then it nests. Open bracket phase level equals, quote, one quote name equals, quote, prime uncle entity, quote. Then a role tag that says the linguistic glitch. Then kernel specs that say spiky electric blue hair, oversized thick-rimmed black glasses. And then it closes all those tags.
Now consider the mechanical advantage of this structure. We are no longer just teaching the model the word prime. We are mathematically mapping a relationship.
Okay, explain that. How is it a mathematical relationship?
Well, the model learns that prime is nested within a phase level 1 tag, which is entirely encapsulated by a module v1 tag. It learns that kernel specs strictly define the physical reality of the role.
Right.
We are teaching it a strict, nested hierarchy of existence.
I love this concept. The user in the source notes talks about having this massive aha moment right here. They realize that by structuring the training data, this way defining environmental triggers, character states, nested modules, they aren't writing a story anymore.
No, they're writing code.
Exactly. They are functionally writing an operating system using language. The XML tags act as system prompts, and the nested modules act as conditional logic engines.
Bit of a profound realization. You are using the syntax of a markup language to force a neural network to behave like a state machine.
This is so smart.
But there is a massive technical roadblock between formatting this XML and the model actually understanding it. And that brings us to the tokenization pipeline.
Oh man, here's where it gets really interesting. This is where things get intensely technical, but it's just so crucial to understand. The source blueprint specifically calls out that standard massive language models use something called subword tokenizers, like BPE, right? Byte pair encoding.
Yes, BPE is the industry standard right now.
But our tiny model absolutely cannot use BPE. It uses character-level tokenization instead. And I was reading this thinking, why? If BPE is the industry standard for the big guys, why does it break our tiny universe?
It comes down to how a machine actually translates human text into numbers it can compute. A tokenizer is essentially the model's dictionary.
Okay.
Now, byte pair encoding is incredibly efficient for standard human languages. It scans a massive corpus of text and groups frequently occurring sequences of characters into single tokens.
So it chunks things together.
Right. For instance, instead of seeing the word playing as 7 distinct letters, BPE might recognize play as one token and ing as another. It compresses the data beautifully.
Which is great if you're reading Wikipedia or parsing a news article.
Yes, but our model is not reading standard English. It is reading highly specific custom XML tags.
Right, the firmware formatting.
Exactly. If you apply a standard BPE tokenizer to our dataset, it encounters our custom tag, say, open bracket, module ed equals. Because BPE has been trained on standard internet text, it has never seen that exact sequence of characters before.
Oh, I see where this is going.
So it panics. It chunks it in a way that makes statistical sense to standard English, but completely butchers our syntax. It might split it into the token for the open bracket plus mod, then another token for UL, and a third token for ed.
And suddenly, the fundamental logic of our firmware is just destroyed. The model doesn't see a neat mathematical container anymore. It sees shattered fragments of brackets and random letters.
Exactly. And if the syntax is broken at the foundational level, the firmware cannot execute. The tiny model cannot rely on generalized subword chunks. It must learn the exact structural grammar, bracket by bracket, space by space.
It has to know the exact spelling of the code.
Therefore, the blueprint dictates character-level tokenization.
So we literally take our entire XML-wrapped text file and we build a custom alphabet from scratch. The Python code provided in the sources is actually beautifully simple here. It just scans the entire Necronomicon corpus.txt and pulls out every unique character it can find.
Every single one.
Every capital letter, every lowercase letter, the numbers, the angle brackets, the equal signs, and even the spaces.
The code then maps each of these unique characters to a specific integer. This is handled by 2 dictionaries in the Python script. They're called stoi and etos.
Okay, so stoi meaning string to integer.
Correct. When the model reads the text, stoi translates the opening bracket into, say, the number 1. The letter M becomes 2, the letter O becomes 3, and so on.
So it's just converting the text into a giant array of numbers.
Yes. The model only ever does math on these numbers. It doesn't know what a letter is. Then, when the model generates its own output, the etos dictionary integer to string translates those calculated numbers back into human-readable characters.
The blueprint notes that when this script runs, it prints out Necronomicon vocabulary size, 65 unique characters.
Just 65.
That is staggering to think about. The entire universe of the Clockwork Necronomicon, every piece of lore, every kernel panic, every state change is constructed from a fundamental alphabet of just 65 building blocks.
It's the periodic table of this specific universe. And once that custom vocabulary is locked in, the pipeline performs one final critical step before the architecture phase begins.
Right, the data split.
Exactly. It slices the tokenized data into 2 distinct arrays. It takes 90% of the data and places it in an array called train data, and the remaining 10% goes into val data, or the validation data.
And this is basically to prevent the model from just cheating on the test, right? We want to make sure it's actually learning the underlying grammar of the XML and the vibe of Prime the Glitch, rather than just memorizing the exact comic book panels word for word.
Yes, it's about checking its work.
We train it on the 90% and then test its understanding on the 10% it was never allowed to look at.
It is the difference between rote memorization and true generalization. If the loss, which is the error rate, goes down on the training data but goes up on the validation data, well, The model is just memorizing and failing to understand the underlying rules.
It's overfitting.
Precisely.
Okay, so we have our raw materials. We extracted the OCR text. We forged it into an XML firmware structure. We broke it down into a 65-character mathematical alphabet. The data is completely ready. Now we have to build the physical brain that will process it. We need to architect the custom tiny transformer.
And the blueprint utilizes PyTorch to construct this, specifically a decoder-only transformer.
Okay, so if I'm understanding this right, a decoder-only transformer isn't like a search engine. It doesn't take a query, go look up a fact in a database, and return an answer.
No, not at all.
It has one singular obsessive function, right? Based on the sequence of tokens it has seen so far, it just predicts the mathematically most probable next token. It's essentially the world's most complex, context-aware autocomplete.
That is the perfect way to describe it. It is autoregressive. It predicts the next character, appends that new character to its context, and then uses that new, slightly longer sequence to predict the next character over and over again.
It just loops.
Yes, but to do this effectively, especially with complex XML syntax, the architecture needs specific constraints. We define these constraints through hyperparameters.
Hyperparameters. These are the literal settings of the brain. They define the size, shape, and memory capacity of the neural network.
They dictate everything about how it processes information.
Right. And because we are building a tiny model, we are looking at an architecture of maybe 100K to a few million parameters total. I mean, you can compile and run this on the CPU of the laptop you use to watch Netflix.
It's incredibly accessible.
It really is. So let's break down the specific settings from the PyTorch blueprint. The first one is block size equals 64.
The block size dictates the context window of the model.
Okay, let's use an analogy here for you listening. If the parameter weights are the model's long-term memory, the concepts it has learned over time, the block size is its short-term working memory.
That's a good way to frame it.
So when the model is trying to guess the next character, it is only allowed to look back at a window of the previous 64 characters. Anything that happened 65 characters ago is entirely invisible to it in that exact moment of prediction.
That is exactly how it functions. And the blueprint explicitly justifies this specific number. 64 characters is just large enough to capture the full scope of a standard XML tag and its immediate attributes.
Right, because if we made the block size too small, say like 10 characters, the model would suffer from chronic short-term memory loss.
It wouldn't hold the context.
It might see IDs 1 and try to predict the next word, but it would have completely forgotten that 15 characters ago it opened a module tag. It wouldn't know it needs to eventually generate a closing module tag.
Yeah.
The whole firmware structure would just collapse.
Precisely. The context window must be wide enough to encompass the structural dependencies of your data. The next hyperparameter is nemd equals 128. This defines the embedding dimension, or the vector space, of the model.
Okay, this is a concept that always bends my mind a little bit. The blueprint notes that nemd is set to 128 to handle the rich lore metadata. Explain to us how a wider vector space mathematically helps a model understand something as abstract as lore.
Sure. To understand embeddings, you really have to imagine a multi-dimensional map. When a token enters the model, it isn't just a flat number anymore. It gets projected into this space as a coordinate.
Okay, a coordinate.
If nemd was set to, say, 3 dimensions, you could visualize it as a dot in a standard room, an X, Y, and Z axis. The model tries to group related concepts close together in this room, so gravity and suggestion might be placed near each other in the corner of the room.
But with only 3 dimensions, the room gets crowded really fast, doesn't it? Everything starts overlapping, and the model loses nuance. It can't distinguish between the concept of gravity and the literal word gravity.
Exactly. The mathematical distance between concepts becomes muddy. But by setting nemd to 128, we aren't working with a 3D room anymore. We are working with a 128-dimensional geometric space.
Which is impossible to visualize, but mathematically huge.
Right. The model has vastly more mathematical room to store incredibly complex nuance associations. It can isolate a specific dimension that correlates to spiky electric blue hair and definitively link it to the prime entity while keeping it entirely separate from the uncle entity module.
It gives the lore the geometric space it needs to be distinctly defined. I love that. It gives the universe room to breathe mathematically. That is beautiful.
It is elegant math.
Okay, then we have the processing units. We have batch size equals 32, unlayer equals 4, and n head equals 4. The n head refers to the multi-head self-attention mechanism, right?
Yes. Attention heads are how the model determines which parts of the 64-character context window are actually important for predicting the next character.
Okay, so If we have four heads, they can essentially split the labor. One attention head could act as the grammar checker, fiercely focusing on the angle brackets and equal signs to ensure the XML syntax remains perfect.
Yes, a structural focus.
Meanwhile, another attention head acts as the lore master, totally ignoring the brackets and focusing entirely on making sure the kernel specs align with the role established earlier in the text. They look at the same 64 characters, but pay attention to entirely different relationships.
And that division of mathematical labor is precisely what allows even a tiny transformer to generate highly structured, contextually accurate output.
It is genuinely marvelous how accessible this technology is when you strip away the hype.
It really demystifies it.
Yeah. We aren't talking about proprietary black box algorithms hidden in a Silicon Valley bunker. We are talking about clearly defined hyperparameter integers, explicit vector dimensions, and division of processing labor all running locally.
It proves that generating emergent complexity does not strictly require massive scale. It just requires elegant constraints and deliberate architecture.
Okay, so the PyTorch classes are coded, the mathematical alphabet is set, the brain is architected. Now, we arrive at the spark of life, we compile the script, and we enter phase 4, the training loop.
This is where the model actually learns. We take our train data, slice it up into batches of 32 sequences at a time, because that's our batch size, and we begin feeding them through the transformer blocks. The blueprint specifies running this loop for a maximum of 3,000 iterations.
So break down the mechanics of what is actually happening inside the machine during those 3,000 loops. Because, like, at iteration 0, this model knows absolutely nothing, right?
Right. At iteration 0, all of the parameter weights, the connections between the neurons, they are completely randomized.
Pure static.
When you feed it the first sequence of characters and ask it to predict the next one, it is essentially guessing blind. It will spit out absolute garbage, just random letters and symbols.
But every time it makes a prediction, the system grades it. It uses a loss function. The blueprint specifies cross-entropy loss. Let's unpack that because it's the engine of learning here.
Cross-entropy loss is mathematically quantifying exactly how wrong the model's prediction was compared to the actual next character in the training text.
So it's an error score.
Yes.
Yeah.
If the model predicted an X, but the actual next character was a closing bracket, the loss function generates a high error score. It calculates the mathematical distance between the model's bad guess and the true target.
So we have a massive penalty score. How does the model use that score to actually get smarter?
It uses an algorithm called backpropagation, which is driven by an optimizer. The blueprint specifically calls for the Atom W optimizer.
Atom W. Okay, let's use another analogy here to explain Atom W. Imagine the model is a hiker trying to find the lowest point of a massive, dark valley, the absolute minimum error rate. But it's pitch black, and they can only feel the slope of the ground beneath their feet.
Right, and that slope is the gradient calculated by the loss function.
Exactly. A standard gradient descent optimizer would just take a step downhill. But the terrain of a neural network is incredibly complex, right? There are false valleys, jagged cliffs, and weird flat plateaus.
It's very easy to get stuck in a suboptimal valley.
Right, so the Atom W optimizer acts like a hiker with a sophisticated momentum tracker and adaptive footwear. It remembers which direction has been consistently downhill and builds momentum so it doesn't get stuck in a small ditch.
It carries its velocity forward.
But it also adapts its step size, the learning rate, based on how steep the terrain is. If it's a steep cliff, it takes tiny, careful steps so it doesn't accidentally overshoot the bottom of the valley.
And we should note, the W in Atom W stands for weight decay. This is a crucial regularization technique.
What does that do?
It essentially penalizes the model for relying too heavily on any single parameter weight. To use your analogy, it prevents the hiker from putting all their weight on one leg.
Oh, that makes sense.
It forces the network to distribute the learning across the entire neural architecture, which prevents the model from just memorizing the training data. It forces it to generalize the underlying rules.
So over 3,000 iterations. Taking these calculated steps down the loss gradient, adjusting millions of tiny weights ever so slightly, the model actually learns.
It finds the bottom of the valley.
It stops spitting out random letters. It learns that if it sees a closing angle bracket and a slash, the mathematically optimal next character is almost always going to be the name of the module it is currently inside. It learns that the word keiju transitions reliably to engaged.
It builds an internal statistical universe of the Necronomicon syntax and Prime's mental state.
And you witness this culmination in the generation phase. The training loop finishes, the weights are frozen, you are ready to test the engine.
The blueprint shows us exactly how to pull the ripcord here. We provide the model with an open tag a seed sequence. We feed it start string equals open bracket module ead equals quote v1.
We give it the first few notes of the melody, and then we just ask the transformer to generate 300 brand new tokens autonomously.
You are asking it to extrapolate the universe.
And it does. It hallucinates perfectly. It spits out brand new, syntactically flawless XML nodes. It opens tags, nests phases, invents lore-accurate kernel specs that literally never existed in the original comic panels, and perfectly closes every tag it opens.
It has completely internalized the firmware.
It knows how to construct a valid entity, how to assign a role, and how to invent attributes that fit the established irreverent aesthetic. It is a massive technical triumph.
It really is.
It is deeply awe-inspiring. I mean, we took random visual art, stripped it to chaotic text, forced it into an XML structure, built a custom 65-character mathematical alphabet, architected a PyTorch transformer, navigated the Lost Valley with Adam W., and now we have a machine that dreams in localized lore.
Yes, but...
Generating the script is not the same as putting on the play, right?
Exactly. Generating a perfectly formatted XML string that just prints out on a computer terminal is incredibly cool, but it doesn't do anything. A text generator is just a text generator.
Right, it's inert.
If the Clockwork Necronomicon is supposed to be a state machine, an actual engine that drives a localized universe, we are missing the execution environment. We need a system that can take that generated XML, parse it, and use it to drive actual states and actions.
You need an operating system capable of running a waking dream. Which brings us to the final and undoubtedly the most complex source document in our stack, the Wake-Mux Theatrical Engine System Instructions.
This document is, well, it's something else.
When I first read this document, my brain completely short-circuited. It is a masterpiece of system architecture, completely disguised as high-level literary criticism.
The premise is staggering. The author of the source notes looked at James Joyce's novel, Finnegan's Wake, and realized it wasn't just a book.
Right. For those who haven't tortured themselves in a graduate literature seminar, Finnegan's Wake is notoriously one of the most difficult pieces of literature ever created. It doesn't use standard English. It uses this, dream language composed of polyglot puns, portmanteaus, and cyclical logic.
It is deeply opaque.
And it famously begins mid-sentence and ends with the first half of that same sentence, creating an infinite non-terminating loop.
It is an unconstrained, cyclical state machine in book form. And the genius of the Wake-Mux document is that it maps Joyce's chaotic, overlapping archetypes into a concurrent, multi-threaded multiplexer architecture.
They designed an asynchronous software kernel to decompile a hallucination, and this is the exact execution engine we need for the Clockwork Necronomicon.
It fits perfectly.
If our tiny PyTorch model is dreaming up these dense, chaotic XML lore nodes, we can't just print them to a screen. We need to feed those raw tokens into the Wake-Mux engine to actually bring them to life.
So let's dissect the mechanics of how this engine operates, because it is brilliantly rigorous. It begins with the 4-channel multiplexer. Now, a multiplexer is a device that takes multiple input signals and routes them into a single output line.
Okay.
In this engine, every piece of generated XML from our tiny model must be dynamically parsed and assigned into one of 4 simultaneous execution threads, or theatrical roles.
4 concurrent channels processing the dream. Let's look at channel 00. The document labels this ALP, aligning with Joyce's character Anna Livia Pluribel. Mechanically, this is defined as the asynchronous carrier wave.
Yes. The system instructions define channel 000 as handling fluid dynamics, background recursion, and data cleanup. It is the river of the system.
Your river, okay.
If we plug our tiny model into this multiplexer, any generated XML attributes that relate to ambient environmental lore, passing time, or background noise would be routed to channel 00. It is the constant flowing baseline of the simulation.
Flowing right alongside channel 01, which is HCE, Humphrey Chimpton Earwicker. The blueprint calls this the core baseline hardware.
Right. If ALP is the river, HCE is the city built on its banks. This channel processes rigid structures, systemic boundaries, and physical blocking.
So when our tiny model hallucinates a node that says gravity is just a suggestion, the multiplexer has to resolve that statement. The concept of gravity is a rigid physical law, so it gets processed by channel 01 HCE. But the idea that it is a suggestion implies fluid rebellion, which might cause a conflict with channel 00 ALP. The engine is instantly creating dynamic friction out of the text.
And where there is friction in a system, there are bound to be errors. Which brings us to channel loser 2, Shem, the exception logic.
Ah, this is where Prime the glitch lives. Shem is the exception handler. The instructions explicitly state that this channel is responsible for generating runtime anomalies, linguistic mutations, internal bugs, and chaos. It literally breaks the fourth wall.
Whenever our tiny model generates high-entropy strings like iguana on a stick or Caillou mode, the multiplexer routes the data directly to channel O2.
It embraces the chaos.
It does. It gives the chaos a designated, isolated execution thread. This is a brilliant system design because it prevents the chaotic hallucinations of the language model from crashing the entire application. The chaos is expected, and it's handled.
It's contained, but only because it is fiercely counterbalanced by the final thread, channel O3. Sean, the UI compiler.
The authoritarian grammar protocol.
The structural cop. While Shem is trying to mutate the system, Sean enforces rigid validation, formal UI interfaces, and strict narrative logic. Channel O3 looks at the incoming XML and demands that it conforms to the rules.
So in real time, the tiny model generates a lore node. The Wake-Mux Engine catches it and simultaneously fractures that data into background ambience, physical laws, chaotic exceptions, and structural formatting, running all 4 threads concurrently.
It's breathtaking. But the Wake-Mux Engine doesn't stop there, does it? Once the data is routed through the multiplexer channels, it must be projected through the 3-tier registry matrix, the scales of reality.
The mandate here is that a single action must reverberate across all scales of the universe simultaneously.
The document breaks it down into 3 tiers. First, the macro scale. This is the cosmic mythic level of the simulation. In a theatrical sense, this dictates the lighting, the massive set design, the universal cycles.
The big picture.
Right. Then we have the mesoscale. This is the social geography, the literal spoken dialogue, the immediate local history.
And finally, the microscale, the somatic cognitive level. Physical tics, isolated neural spikes, localized hardware memory access.
Okay, let's apply this to an output. Say our tiny model generates an XML line where Prime picks up a soldering iron. The Wake-Mux engine forces that single text string to execute on 3 levels.
All at once.
On the mesoscale, Prime physically picks up the tool. But on the microscale, the engine might execute a cognitive tick-a-twitch in Prime's spiky blue hair or a memory fragment about a burned finger. And on the macro scale, the engine might slightly shift the ambient lighting of the entire localized universe to reflect the heat of the iron.
It takes flat 2-dimensional text generation and inflates it into a fully rendered 3-dimensional state simulation. It forces depth, but this level of complexity introduces a massive systemic risk.
Oh, absolutely.
What happens when the tiny language model, which is fundamentally just predicting characters, hallucinates something too dense? What happens when the nested XML tags become so convoluted that the multiplexer cannot resolve the conflicting threads between Shem's chaos and Sean's structure?
We've all seen standard language models go off the rails. They hit a logical loop and just start spewing infinite garbage text. In a normal application, the program just crashes and you have to force quit. But the Wake-Mux engine has a built-in survival mechanism for this.
The Thunderwords.
The Thunderwords. Kernel panics. This is perhaps the most brilliant translation from Joyce to computer science in the entire document.
In Finnegan's Wake, Joyce peppered the text with 10 massive 100-letter Thunderwords. In literary terms, they signify a massive societal fall or a cosmic shift. The Wake-Mux system instructions take this literally.
They repurpose it.
They repurpose the Thunderword as an aggressive garbage collection protocol.
The engine constantly monitors the thematic density and the error rate of the multiplexer threads. If the tiny model's generated XML reaches a critical mass of chaotic complexity, if it generates a paradox that the engine cannot execute, the parser intentionally drops out. It triggers a Thunderword event.
A massive extinction-level auditory and visual cue that clears the current stage stack.
It intentionally crashes the 4-channel multiplexer. It sweeps the board clean and reboots the entire localized simulation into a new epoch, resetting the environment and the characters back to a primal baseline state.
It is a self-healing mechanism. Left to its own devices, an unsupervised language model generating text infinitely will eventually degrade into static.
It's inevitable.
The Thunderword anticipates that degradation. When the universe becomes too corrupted by its own lore, the engine wipes it clean and allows the model to start dreaming again from a clean slate.
Which brings us to the final beautiful rule of the Wake-Mux engine, circular memory optimization, the infinite loop.
The mandate that the system must never truly terminate.
Just like the book, the engine requires that the final generated fragment of an epoch must seamlessly splice back into the initialization parameter of the next epoch. The end of the universe feeds directly into the Big Bang of the next.
If we pull all of these pieces together, we have successfully outlined a technological marvel. We've transcended the concept of an AI chatbot. By taking a tiny, custom-architected PyTorch transformer trained purely on OCR-extracted comic book data, constrained heavily by XML firmware, and plugging its output directly into the multi-threaded, self-resetting Wake-Mux theatrical engine, you have built something entirely new.
You have built a non-terminating state machine. Let's recap this journey because it is staggering. We started with chaotic visual art pictures of a comic book. We built an OCR accessibility pipeline to destroy the art and extract the text, harvesting the irreverent soul of Prime the Glitch.
We then forced that chaotic text into a highly rigid XML firmware structure, teaching the model hierarchical relationships. We circumvented standard subword tokenizers by building a custom 65-character mathematical dictionary, ensuring the syntax would never be chunked improperly.
We defined the hyperparameters of a tiny decoder-only PyTorch brain. We widened its vector space to 128 dimensions to give the lore mathematical room to breathe. We fed it data in batches of 32 and sent it on a 3,000 iteration hike down the dark valley of cross-entropy loss, guided by the AtomW optimizer, until it learned to hallucinate perfect, lore-accurate XML nodes.
And finally, we solved the execution problem. We took those hallucinated nodes and fed them into an asynchronous operating system based on James Joyce, routing the text through concurrent channels of fluid dynamics, rigid hardware, chaotic exceptions, and UI structure, all monitored by apocalyptic kernel panics and infinite memory loops.
It is a breathtaking synthesis of deep learning, high-level systems design, and experimental literature. And it leaves me with one final, deeply provocative thought for you to take away.
What's that?
Well, we have been so heavily trained by the current tech landscape to view language models through an incredibly narrow utilitarian lens. Ask a question, get a summary, write a prompt, get an email.
We view them as subservient tools meant to increase our personal productivity.
Exactly. We demand that they be useful. But this deep dive proves that the underlying neural architecture is capable of being so much weirder and honestly so much more profound. They can be utilized as independent, non-terminating state machines. So I want you to imagine the scenario we started with.
The USB stick.
What happens when your computer is running a tiny, infinitely looping model of a universe in the background? It's completely disconnected from the internet. It doesn't want to help you write code. It doesn't want to summarize your PDFs.
It exists purely to sustain its own complexity.
Yes. It is just sitting there on your CPU, experiencing Thunderword kernel panics, managing cosmic scales of reality, generating chaotic exception thread lore, and quietly dreaming to itself, endlessly looping in the dark.
It forces us to reconsider the fundamental nature of what we were building. When we stop trying to force these models to be helpful assistants and start allowing them to be systemic engines, the possibilities are genuinely limitless.
It's a wild, beautiful thought, a tiny, dreaming universe on a cheap processor. Thank you so much for joining us on this deep dive into the Clockwork Necronomicon. We'll see you next time.